So today is the last session, last lesson for me. I'm going to tell a little bit about the computational part of computational linguistics and how we can design and implement Sanskrit computational linguistics on a computer. So first part is what is a computer. So in 10 minutes I'm going to tell you what a computer is. And we start from basics. Yes, last time we saw in a little bit of information. What is information? Remember tossing the coin? Okay. And then I told about the unit of information. What is the unit of information? Not that word. It's smaller. The unit of information. See, I was tossing a coin. I said, you know, when the coin is turning, this is random. When it lands, it's heads or tails. 0 or 1, left or right. This is the basic unit of information. How is it called? No? Nobody remembers? Unit of information? No? It's the unit of data. It's a unit of data. No, it's smaller than word. Very small. It's a bit. Bit. Last time we saw bit. It's 0 or 1. And then we saw byte. Byte, 8 bits. So you can put character in a byte. The bit is the information that you get when you get the answer to a yes-no question. Okay? You can get a lot of information by asking yes-no questions. This game with kids that we play when I'm driving in the car, and we think in our head of some person. Yes? And the kid can ask questions, yes or no. You know, is it a man? Is it a woman? Lives in France? Doesn't live in France? Yes, no, yes, no, yes, yes, no. Okay? And if you know how to play the game well, then you will get the answer in less than 10 questions. Yes? Why? See, was the first question. Okay? If it's just telling whether it's male or female, 1 bit is enough. You just ask the question, you get the answer. That's it. Yes? Then, you know, is she older than 50 or younger than 50? Yes, no. So now we have 4 possibilities. See? We have 2 possible answers. After 2 questions, there are 4 possibilities. After 3 questions, there are 8. After 10 questions, how many possibilities? Much more than 64. 64, 6 questions. 128 is 7. 266. 512. 1024. That's 2 to the power 10. Okay? So you can store any number between 1 and 1000. So, variety of game. I think of some number between 1 and 1000. Yes? How many questions do you need to guess exactly the number? Any guess? I think in my head, some number between 1 and 1,000. Okay? Now you ask me questions about this number. You know, is it greater than 10? Is it less than 7? Only questions by yes and no. Okay? How many questions do you need to ask me to know exactly what is the number? You can ask me a question, is it 1? Is it 2? Is it 3? Is it 1,000? This is stupid. Stupid. Yes, because in average you will need 512 questions. 500 questions in order to guess, see? If you're lucky, you'll get it sooner, but in average you'll need 500 questions. But if you ask the right question, how many? Yes, sir. 10. Very good. You get a grade of 10, sir. 10. Why? Because the good question to ask is your number less than 500? When I say yes, you ask, is your number less than 256? Okay, if I say yes, so you cut in half every time. And for sure, you'll get the answer in less than 10 questions. Okay? So see, this is the power of this exponential. It doubles that every time. Remember the chessboard with the rise. See? So these numbers go very fast. So the game that I play with my children, they will get it with less than 10 questions. Yes, why? Because there are less than 1,000 people that we know, both of us, that are interesting for this game, yes? Okay, now we have the bit, we have the byte, so we put 8 bits together, you know, it's like peas in a pod. And then you can represent one character. And then you put bytes, one to next to the other. So in the old days, like 30 years ago, we would design computers with a notion of word that was 4 bytes. 4 bytes, so how many bits? 4 bytes. How many bits? 32. 32 bit. So it's 32 bit. So it's 32 bit. I can put a quantity of information of 32 bits. That is, I can represent a number between 1 and 2 to the 32. What is that? It's hard to imagine 2 to the 32, but we saw that 1,000 was approximately 2 to the 10, what you can represent with 10 bits. And 1,000, it's 10 to the 3. Okay? So you can use this in order to get some idea of what is 2 to the 33. Yes? It's about 4 times 2 to the 30, and 2 to the 30, it's what? It's 1,000 of 1,000 of 1,000. It's 1 million. See? Big. 4 million. When you have 1 million rupee, are you a millionaire? Oh, in India they don't have millions. You have lakhs, you have crore. A millionaire is crorepati. Slumdog millionaire? Crorepati. Yes? Now, that's a computer world. So it's one unit. And I can put a big number, but I cannot do much more than that. So a computer memory is just putting words next to each other. This is computer memory. How many do you put? Well, how many do you put? If you say, okay, my word is 32 bits, then I'm going to put any information in it. Information is just a bunch of zeros and ones. But you can interpret it as data, like some number. You can also interpret it as some address to go in the memory and fetch more information. Okay, so that's very important to have this duality between data and addressing. So you can use here this content 0, 1, 1, 1, 1, 1, 1 as some addressing here. 0, 1, 0, 1, 0, 1, 0, 1. See? Addressing is like going here, asking questions, where do you want to go, where do you want to go, and then you go to one memory word. Okay. So, how many words do you need in your memory to use fully the fact that you have 32 bits in your address space? See, I'm using this as an address. I'm using each bit among the 32 to answer the question, should I go left or should I go right in the memory? Okay? And I asked this question 32 times. So what is the size? What is the size? See? How many possibilities do we have?
64.
More than 64?
256.
More than 250. I see one hand raised here. All right. Yes, sir.
If you give adequate chances, they will get the correct answer. The way we have guessing.
Okay, but I've got only 1 hour. You can guess the question by asking yes or no question. You know, is it greater than 32? Is it greater than 6? See? All right, sir.
2 to the 32nd.
Yes.
2 to the 32nd power.
2 to the 32, because you're asking a question yes or no 32 times, so it multiplies every time.
2 to the power of 32.
Yes, 2 to the power of 32. And we have it here, see? It's here. 4 million. 4 megabit. 4 million. 4 million words. Oh, that's a lot. That's a lot. That was a big computer 30 years ago. You know, I was programming on such a computer, and I thought, oh my gosh, you know, this is so much memory, so much data, so many possibilities. Nowadays, this is 2 to the 32 bits. Yes? Very small. So you've got much more in a mobile phone, and still more here. But you get the general idea. Now I can play with my computer, I can put zeros and ones. I can read, I can write. I can jump, because I can interpret a word as an address, so I can say, oh, okay, go here, inspect, read. I can take decisions according to a bit. You can say, you know, can I go there or there? So this way, you go at one place or another. Then you can encode these various operations, jumping, looking, adding. And you can encode these various possibilities as the instructions of the computer. And these instructions you can store in the memory as well. So this is a universal computer. You can manipulate data, and you can interpret data as some kind of programming. That's all. Now you know what's a computer. So you must be very surprised because you thought, oh, he's going to teach us what's a computer, he's going to tell us about electronics, about, circuit boards and gates and silicon and I don't know. No. This is software. It's just manipulating information in an abstract way. We don't care how the computer is implemented. It's another question. If we didn't have electronics, I could play the computer game otherwise. I could play it with coins. Give me 10 crore rupees, okay, in coins. That's a lot. Yes. So if I have a room that is big enough, I'll put my 10 crore rupees, one after the other, in rows. I will put 32 rupees. Yes, and if the hole is long enough, I will have 4 million rows, and that's it. Now I can walk in the computer, I can flip the coins. Here, there, here, there. This will do exactly the same thing as operating the computer in electronics. See, it's irrelevant, the medium. Technology, electronics, whatever will come, does not matter. What matters is information, the way you manipulate it, the way you ask questions, the way you store information, the way you represent knowledge with a computer. You can compute with rupees as well as with electronic bits. So all the rest is just having some kind of basic representations that we call data structures, how to organize information in a more interesting way than just a byte or a word. Any question? Is it clear? The first data structure is the list. List, in mathematics it's called a sequence. It's having items one after the other. This is a list. So I have the list, for instance, of, of prime numbers, maybe even numbers, 2, 4, 8, 16, 32. Okay, so how am I going to represent that? Well, every element of the list must be able to store the maximum number. Okay, so let's imagine it's the computer word, so it's 32 bits, so you can store numbers up to 4 million. So that's good enough. And then you can use the rest to have a representation of where is the next element in the list. And here I'll put some kind of marker saying the list is finished. Okay? So you see? Now with this little trick of using part of the word as data and part of the word as address, I have an interesting data structure which is list. So now I can have some program that will look in sequence every element in the list. Since we have basic arithmetic operations, adding, multiplication, division, and we can, for instance, take half of each of these even numbers, and so half of 2 is 1, and half of 4 is 2, and then I get 4, then I get 8, then I get 16. And at the same time, as I divide, I construct a new list. So from my list of even numbers, I get the list 1, 2, 4, 8, 16. It's not the list of even numbers, it's a particular list which is the powers of 2. Yes? So here are the halves. So here is the list X, here is the list Y. And then we have programming languages that will give you possibility of naming things, of storing things, and so on. So I can write a program, let X be a list of integers, a list of numbers, compute the list of halves of these numbers, and it will just do this kind of operation. Okay, so this is programming. This is programming. It's the essence of programming. A list is the simplest data structure, but it's already powerful enough to represent, let's go to linguistics now. We saw the basic units of linguistics. Yes, the phoneme, then the word, then the sentence, then the discourse. So you just need more memory and a little bit more structure in order to represent that. But now we understand that in a computer world, we can represent a phoneme. Yeah, there are only 50 phonemes, so you don't need that many bits to represent a phoneme. Now, you can represent a word by putting one phoneme or one letter in every slot of your list. Okay? So if I say, I want to represent Deva, for instance. Okay? So what is it? If we think of Sanskrit, Panini, Pratyahara, or is first, so we'll give it number 1. Yes? Then you have all the vowels. Then A will be 10. Okay? Then D will be, I don't know what, 32, something like that. And then V will be, 48. Okay? So I have an encoding of my phonemes as small integers that I can represent in a word. And now I can represent the word Deva as a list of phonemes. 32. 10, 48, and 1. And then the links. Okay, so this word W is a representation of Deva. Okay? So it's some kind of internal representation, but from outside I can say it's Deva. Have this mapping as part of mapping from the outside. Like if you're typing Devanagari, then you will recognize D, and then you say, okay, this is 32, and so on. So conceptually, you just think of your word as being Deva. One letter in every element of the list. Okay? So now we know how to represent words. Yes, it's as simple as that. I want to do some let's do Devaha. Devaha. H is, I don't know, 49. Then I have some other word. This is W1. W2 is what? Oh, it's our good friend Vanam. Yes? So I have Devaha, Avanam. Now I want to put the two together. Oh, I need to compute Sandhi. So how do I compute Sandhi? I go to the end, I travel in my list until I get to the end. Yes. And I look at the end here, and I look at the beginning of W2 here. And I look, is there some Panini Sutra that matches, that tells me when I have this end of pada and this beginning of pada, what should I do? Devo Vanampa Gacchati. How are we going to get it? We are going to get it because there is a Panini Sutra that says that this and this combine to make O. Okay? So that's it. Now I just have to redirect this here and this here and have a word W, which is the sided form of putting the two words together. See? So it's as simple as that. For a simple operation like Sandhi, of course you will tell me, oh, but how do you look Panini with the computer? You know, the computer is not going to turn the page of Ashtadhyayi until it finds the right sutra. So you have to put the sutras themselves in the computer and instruct the computer how to look for sutra, how to do the matching of your word with the sutras. It's not too hard because Ashtadhyayi is very well organized. It's very precise. It's very well organized. So you just enter it and you have a computer program that will look and that will make the operations, basically. When you have a sutra that says, if the meaning of this word is this, then you do that, otherwise you do something else, then that's harder, yes? You have to scratch your head. How are you going to deal with this situation? Yes? Because representing the meaning is not that easy. So you have represented words here, yes? How would you represent the meaning? How would you represent the concept of deva? See? This is much harder. So if it's too hard, then we don't give up. We don't give up, but we say, okay, we don't know how to represent this, whether the word is in this sense or in this other one. So we'll keep both possibilities. Yeah? So it's like, you know, the coin is turning, and you don't know if it's going to land heads or tails. So you take both chances. Okay? So you have two ways. Either you do it one way, or you do it the other way. So that's non-determinism. See, I talked about determinism. You do one operation after a time. But you can also do non-determinism. When you don't know, then you take both possibilities. And maybe one possibility will be wrong, so you will have to backtrack, to go back on your decisions and take the other solution. The same way as I explained how to get to the treasure in the museum. Okay? Now that we have lists, we have more, actually. Because I can represent a list each of element of which is a list itself, a list of lists. Aha! So here I have a list, and every element of the list is not a number, it's interpreted as the address of some other list. I have a list of lists. And here I can have a list also. See? See what it draws? It draws like a tree. It's a tree, urdhva mulam. Yes, the root is above. Shakaradam. The branches are going down. This is the way we represent trees in computer science. But now we can represent very interesting knowledge using this data structure. See? Because in my first list here, I can take a list of 50 elements, 1 to 50, and here I will say, oh, this is A, this is R, this is E. I put all the alphabet. This is D. This is E. This is V. This is A. Oh, look, you have Deva. Ah, see? So it's a different idea. First I said, let's put Deva in a word. So I've put Deva like this. Horizontally. Okay? Now I say, oh, but you can put Deva vertically in new structure where you have lists of lists. Aha! I can put any word like this. I can put all my lexicon like this. One word at a time. Let's do the root Dru. Oh, Dru, it starts with D also. Yes, so it's going to use this same link. But here it will go in R, and then it will go in U, Dru. Okay? And in order to not to get confusion, I will add one bit here, which will say, okay, this is the end. I mean, this word is in the dictionary. Okay? That's it. This is the way to represent the lexicon. Okay? It's not any harder than that. Once you have the list, then you can make the trees. When you have trees, you make forest. Yes? This is Christmas. This is my Christmas tree. So you get the idea. You get more complex data structures, and progressively you get more knowledge in the computer. Computer is dumb. Computer is this bunch of zeros and ones. But you're driving the computer. You're writing the instruction. You say, okay, go down in the tree, one letter after the other. No. Write a new word in the memory. look for this word, go to the end of the word, apply Sandhi. You are doing it. But you are doing it not every time, like with my rupees. You are writing the computer program that will do it once and for all. That will do it once, that will do it twice, that will redo it, that will do it 1 million times in 1 second. So it was big and fast and stupid. But you, with your brain, you write the computer program, you imagine the right data structures. Then you have computer professionals like me, so we make programming languages to ease you the job so that you can designate easily what's a word, what's a dictionary, how to put 2 dictionaries together, this kind of thing. So you have higher level operations, as we say. So you don't have to go down to the bit level. You manipulate higher level functions. Functions in terms of your application. So if you're manipulating Sanskrit, I will give you a programming language with the right data structures and with the right libraries so that you can do the necessary operations for playing Sanskrit Computational Linguistics. Okay? Okay, so word. So I was talking about words in Sanskrit, and as we saw, it's a hard notion. What's a word? Is it pratipadika? Is it pada? These are 2 different things. So are we going to make a lexicon of pradipadikas? Or a lexicon of padas? Or both? Perhaps? Yes. And a word, like word, is so general that it's very easy to make mistakes. Yes, because you have lots of intuitions. Okay, so you confuse notions. So when you are doing programming, you must be extremely precise. You must have very clear ideas in your head. Yes? Don't expect the computer to think for you. Again, the computer is infinitely stupid. So you must have clear ideas. If you have clear ideas, you write a clear program, and the program will execute perfectly and do what you want. It will go in Bhagavad-gītā, it will check the Sandhi, it will undo the Sandhi, this kind of thing. Don't expect the computer to tell you the meaning of Bhagavad-gītā. Yes, this is too hard. But we can do simple things, like spell checking, this kind of thing. In order to illustrate the difficulty of the notion of word, I have put here a shloka. And excuse my bad pronunciation of Sanskrit. Purnamada, Purnamidam, Purnat, Purnam, Udachyate, Purnasya, Purnamadaya, Purnameva, Avashishyate. Om Shanti, Shanti, Shanti. Okay, in this shloka, how many words are there? How many words are there? Please? 14. 14. Let me count one way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes, yes. Oh. So it's what, 13? 13. Well, maybe it's 13. What we counted is the number of padas. Yes? So, see, this was a trick question. Yes? I said the word is vague. Okay, so here I use this vagueness to trick you. You should not have said 14 or 13 or 20. You should have said, sir, what do you mean by word? Okay? If I ask the question, how many padas? Then yes, the answer is 13. If I ask the question, how many pradipadikas do you need to represent this shloka? What would be the number? No, please. The students. I want the students. How many pradipadikas? Everybody agrees? 7? So let me count. Oh, we need Purna for sure. Yes. And no, that's not what I wanted to say. Padas and 7 Pratipadikas. But if I ask you the number of different padas, see, that's still another question. That's still another question. Yes? Because Purnam and Purnat are different padas. Yes? But Purnam and Purnam are the same pada. See? So even in the questions, how many padas do you have? It's a slightly ambiguous. See? How many padas in the list, or how many padas in the dictionary that I will have to fetch? These are two different questions. See? So if the question is how many lexicalized padas, how many different dictionary address will I need? Yes, then I have to count 1, 2, 3, 4, 5, 6, 7, 8, 9. See? So you have to be extremely precise. See? You have to, what does it mean exactly? How many? What does it mean different? What does it mean word? So, computer design, programming, this is extremely precise. Okay, if you make a slight imprecision, then you will get the wrong answer. See, here we have 3 answers to the same fuzzy question. If you ask precise answer, then you get precise question, you get the right computation. This is because it's hard to do things precisely, that you have all this sloppy software. Sloppy. Yes, all this Microsoft nonsense with bugs everywhere and viruses and all this, this is too hasty programming. Yes? You want to make money, so you write very quickly, then you sell, you say, oh, very nice, yes, give me your rupees. Okay. If you want to give a good quality product, then you have to think it takes more time. And even seasoned professionals like me, we all make mistakes, finding mistakes all the time, so it's hard. So we develop all kinds of disciplines for checking errors and so on. Okay. Now we have at least some basic ideas of what is a computer, how we are going to store linguistic entities in the computer, how we are making computations about these linguistic entities. So it does more of the same. My software, Madam system, Peter Sharp system, it's all just more of the same. So in 5 minutes I can not explain all my data structure and everything, yes? But I can explain, for instance, my Sandhi splitting. See, I showed very quickly how to do Sandhi of two words. Sandhi splitting is the reverse. It's harder. I have this text. Will represent some Devanagari string, for instance. So you have letter after letter after letter. But you don't have blanks that separate the words, like in English. Okay, so its basic operation is to find the word boundaries and then figure out how using padas and using Sandhi. Sandhi is at the juncture of the words. Okay, so here I have some Sandhi. How can I get this sentence from padas glued together with Sandhi? Okay, so this is Sandhi Vicheda. Is how to get from here to a list of padas. So what is given? What is given is the input, the sentence. You read the shloka in the book, you type it in, whatever. Where are the padas? Yeah, I'm looking for the padas in the world. But their input is just the shloka. Where are the padas? Where are the padas? Any hint? This is linked to what I said before. Yes? Didn't I tell you how to represent padas? No? It's a little bit more complicated. Any idea? Christmas? Fir tree? Yes? That's what we saw. How to represent a dictionary with a tree. That's where the padas are. They are not there by some kind of miracle. Computer does not know about Sanskrit. Know nothing. You know, you enter. But once you enter, they are there. You can look them up. Of course, this needs details. I said, okay, you can use this tree, you can use list, you can use list, that's a tree. Now you can put words. Yes? So how do you put padas? It's not the same as this purna Purnam question. Yes, it's what do you mean by word? Is it a lexicon of Pratipadikas? Is it a lexicon of padas? If you look up a Sanskrit dictionary, Aptes dictionary, you're not going to find padas. Only padas you will find are avyayas. Yes? But the dictionary for the nouns, it does not, you don't have an entry for Purnam, another one for Purnat, another one for Purnasya. You have one entry for Purna. Pratipadika. Yes? Okay, so this is the first structure we need to build. Okay, so we go, we enter the dictionary, it's a dictionary of Pratipadikas. And a dictionary of roots, Dhatu. So how are we going to get the padas? We get the padas by computation. We open Ashtadhyayi, it tells us how to get the padas from the Pratipadikas. Yes? Padas, it's a Pratipadika with some features. It's masculine, it's singular, it's tritiya, whatever. Parameters. Using these parameters, the Pratipadika, then the grammar tells you how to make the computation of the suffix. Okay, so it's a little list computation. Then you compute all these padas. And these padas, where do you put them? You put them in a lexicon of padas. So these are initial steps. We have a dictionary of Pratipadikas, like I showed, Deva. Then I instruct my computer, please compute all the padas. So you enter all the rules, all the Sandhi rules. So you need the Sandhi rule for gluing the suffix with the Pratipadika. Then you give all the exceptions, everything. Now it's ready. Now the computer goes ka-chung, 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 ka-chung. And immediately, yeah, it's so fast. Huh? For you, it's been very long to enter all the Pratipadikas. Yes, it took me years to make my lexicon. But building the padas, I press return, and 5 seconds later, I have all the padas. Poof. In similar data structures. Here I have de, vat, de, va, sya. All the padas, they are there. This is the dictionary of padas. And it's very compact. Look, it's very compact. I'm sharing a lot of information, all my padas coming from Deva. They all use the same bits of memory on the common path. So you have lots of saving. Yes? You have exponential saving. So people will tell you, oh, Microsoft technology is so great, so I'm using to use databases, and I will put all my padas in the database, and because databases are big, you know. So, I mean, yes, you can do it this way, but this is not appropriate. Database is absolutely not appropriate for that. Database is appropriate for reservation of plane ticket or this kind of things, yes, because you have some kind of central database and you have lots of people, you know, requesting seats and so on. So you must organize things so that you have no conflict and so on. So it's very complicated machinery. Yeah? We don't need that for our lexicon. Yes? and with this very complicated machinery, so it's going to be very expensive to put a word in a memory, very expensive to retrieve one, and then you have no structure. You just have the words one after the other. Here have the words shared. And I can make computations in the end of the words and so on. So if you think right, then it will be much more efficient, much more convenient. See? Much lighter. Lagawa. Lagawa. This is the driving principle of information manipulation. See? That's why Panini was a genius. It's for the Lagawa. He was able to fit a perfect grammar of the Sanskrit language in a small enough number of shlokas that a human being could learn it by heart. This is a marvel. See? If Panini was alive today, he would be a genius programmer. Yeah. He was a master of information, master of clear thinking. So he would certainly represent lexicon this way, whatever. He would write a new Ashtadhyayi, little bit different. It would be some kind of computer program. Yes? But it would be very short, very concise, very precise. So this Lagawa is sharing here. And then you can play all kinds of other tricks about sharing and so on. So it's very small. It's very small. You can inspect it in very fast way. So it's some kind of check that your thinking is right. Is that the operations are simple and the computer operations are fast. Okay, so now we've got the idea. We have dictionaries of stems, pratipadikas. Then so somehow some human input is necessary to build this. Okay? But that's about it. That's about it. The rest is done by computation. So in my software, for instance, I have this dictionary. Okay, you can enter the dictionary here. No, I don't have 5 minutes. Oops.
I was checking whether.
Okay, it says entry found, Deva. How did he get this? It went in the Pratipadika dictionary, one letter at a time, Deva. Yeah? And then he checked. Yes, it is here. Then I've added a little bit of information. Here I've added a bit of information that goes to the HTML page of the dictionary where you have the Deva entry. Okay? So you can click. So here somewhere on the path, you can click and go here and print the content of the page. The dictionary lookup is just going down in this tree, one varna at a time. So now I click, and here I'm in dictionary. So this dictionary I have made by hand. Yes, at some point, I mean, you have to do input by hand. But I did not write it as a manuscript. Yes, I entered it in a similar data structures and with a lot of information so that you can have these hypertext links and so on. And furthermore, I put this morphological information. Deva, so this is adjective that can be used in masculine, neuter, feminine, with the feminine stem devi, and it means bite. And then you have substantive, masculine, God. So this M, it's information that you have the feature masculine to this pratipadika. So you're allowed to build the padas that correspond to the masculine gender in all number and case. As can be checked. If you click here, you go in the grammarian, and the grammarian gives you the declension table of deva in the masculine. It is masculine. Singular, dual, plural. Nominative, devaha, devam, devena, devaya, devat, devasya, deve, compound form deva, then dual, then plural, deveshu, in the gods. So, see, I started from the lexicon, I search for pratipadika, then I press the button, then I get the padas. I have all the padas here with their indication. Computation is so fast that I don't even need to store it, I can recreate it on the spot. See? You can go here in this interface, you can go directly in the grammarian independently of the lexicon. And then you can say, I want all the padas for pratipadika deva. In masculine, in Roman. Oh no, I don't like Roman, I don't know how to read Roman, I prefer Devanagari. Click on Devanagari. Send. Here it is, all the padas, the same one. Puman, yes, masculine, devaha, devam, devena, devaya, devat, devasya, deve. Same. Same production, same table. It's only at the end of the process. I say, okay, instead of going to Latin alphabet, I go to Devanagari alphabet, and the machine will do the ligature, everything, you know. So it's once you have pieces of software in the library, you can compose things. See? I did not write the software that does the drawing of the Devanagari characters and their ligatures. This is complicated. This is for specific professionals. But I get their software and I use it as a library. I just invoke it. That's it. I don't have to redo the work. Okay? So, when you do programming yourself, you're not going to start from scratch and redo everything. You have to understand, what are the tools you have, what are the libraries, how you can use them, and then you'll do some programming that will link all these tools and do something more. Okay, so now we understand how we get this dictionary of padas. So we are on our way on solving our Sandhi-Vicheda problem. Yes? Because we have the input, the sentence, but also we have this data structure around. It's in the computer. The padas. So here I have devaha. Okay. And here in the same data structure, vanam. Because the sentence is always the same this week, yes? I've abbreviated Devadatta in Deva, yes. So it's Deva Vanam Gacchati. That's what we are splitting. So I have the Deva, I have the Vanam, and I have the Sandhi rules. How do I do? So this is the trick now. This is my algorithm for doing Sandhi Vicheda. I will just give you an indication of how it works. Sandhi rules. What are Sandhi rules? Sandhi rules, they are not arbitrary. Panini did not say, you should merge the phoneme this way or that way in some arbitrary matter. Panini just studied precisely the phonetics of the human organs of voice. Okay, where is your tongue, etc. So you have the notion of phoneme, you have the notion of how you have to move all this physiological system to go from one phoneme to another. After pronouncing one varna, some varnas are easier to pronounce than others. That's why you have retroflexion, these kind of things, yes? It's because in order to go from one varna to another one, you have to spend energy moving your tongue, or closing some cavities, breathing. All this takes energy. Okay? And the basic principle is that you want to minimize energy. You want to minimize energy. This is a general principle of nature. Living systems, they regulate themselves by optimal use of energy. You have trees. Trees have a certain shape. They have a shape that is optimum to get the sun, to get the light from the sun. Okay? So that's why they have certain shapes. This is not arbitrary. It's optimum for the good functioning. In the same way, when we speak, we have some kind of optimization that makes us pronounce one word after another in such a way that we don't spend too much energy speaking. Yes? If you spend too much energy speaking, then you must have more food and so on, more sugar. Yeah. It's not free to speak. When you speak for 1 hour, you're tired. So, Sandhi is linked to this idea of minimizing energy. Let me do a very simple-minded drawing. I will draw some curve which represent the pronunciation of Devaha. Here I have Devaha. And later I want to pronounce Vanam. Devaha, Vanam. See, it's hard here. I have to do all kinds of movements. Okay? So instead, there is some smoothing, some slurring if you want, some smoothing of the sound. And you get Devo Vanam Vyachati. Okay? So here, now this is in the world of phonetics. Here I said phonetics, it's continuous. Yes, because it corresponds to your movement and so on. This is continuous. The phonemes, varnas, are discrete, one at a time. So if you want to draw on this diagram the phoneme, there will be little straight segments like that. Straight segments. And the Sandhi rule is just this triangle. Or V, O. This triangle explains that if a word ended in OHA, and if the next word starts with V, then you remove the H, the rule is actually this way. It's clearer on some Sandhi rules where you remove the right letter, like Tachrutvam, for instance. Tachrutvam, you have the D of Tad that becomes a T, and you have the Sh of Shrutvam that becomes Sh. Okay, so you have here a real triangle. D, Sh, something like that. So these little triangles, they are finite. You have finite number of varnas, you have finite number of beginning of words, of end of words, and so on. And they are listed in the Ashtadhyayi. Yes? That's in the Tripada section. Yes, they are all there. And you have a standard way of writing these triangles. Yes? So we have all these triangles by looking in the grammar. Now we are putting the triangles in this data structure. For instance, in Devaha, the triangle will start not at the end of the pada, but at the last point before the change of Sandhi. That is before aha. Okay? And here, I draw the triangle. Which means I have the data structure, which is the tree, but now it's a little bit more complicated. At every node of the tree, I can put a triangle like this. Okay? So this I do once and for all. I compile. See? So I have the dictionary of padas, I have the grammar, then I make another dictionary-like structure, but with the triangles in. Once I have this data structure, then I know how to do Sandhi Vicheda. I know how to do Sandhi Vicheda because here, at this junction, here I have Devo, Vanam, blah, 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 blah. So I'm reading my word. I'm reading by reading the padas in the dictionary. So I go Dev, and here I see a triangle. So it means, yes sir, question.
Sorry to stop you here. Can I ask something about these data structures, about Sandhi? Are they the direct representations of the Sandhi rules? I mean to say, you cannot store individual cases, right? Devo, and then is juxtaposed with Vanam. That is just an individual case. There could be many more words beginning with word.
Yes, but I don't need to store all the padas, but there's a triangle with the end of words and beginning of words.
So you mean it could be a direct representation of Panini's Sandhi rule?
Yes. Every triangle is a direct representation of the Sandhi rule. Yes. More exactly, a sutra will give you a family of such rules. because you have pratyahara. So pratyahara tells you all these phonemes, they are the same. So the same rule will apply. So a sutra will through the mechanism of pratyahara, will give you several triangles. Okay, but we don't care. It's all such triangles. And I saw them in the dictionary. In the dictionary.
So whenever a string comes, naturally your machine looks into one of these triangles, right?
Yeah, this is what I'm explaining here. Here I'm reading Devo in this structure. But at Dev, at this point I have the triangle. The triangle says aha, V, O. Okay, and this is just above the entry Devaha, it's a Dev. So here I take a decision. I say, oh, maybe Sandhi applies here. Okay, because I have the triangle. Now I look at the upper part of the triangle. The upper part of the triangle must be here. O. Oh, I'm happy, so I move. And here there is no V. Yes, the V is preserved. So it's A and O. So now where do I go? I go to the next word. So I keep looking, but from the top of the tree. Here at the top of the tree, because the rule is not deleting the V. If the rule is deleting the V, then you have a little part here. This little part tells you where to go initially in the words. Okay? So see, every triangle now is interpreted as moves in this structure. Looking up, is there a triangle? If so, is the upper part of the triangle in the input? Yes. Then you look at the right part. Then that tells you where to start, again, looking forward. That's all.
And when two vowels, for example, they get fused and one vowel is generated,
Yes.
like Ramesh, then what is the data structure?
Same. A, U, O. A, A, U, O. A, U, O. Vowel sandhi, consonant sandhi, every sandhi. And these are small triangles. Here it's one or two characters. Here it's at most one character. And here it's one or two. So these are small triangles. Same rule. Now, there may be various ways. We saw that there is various ways of splitting. Yes, yesterday we had this wonderful talk about Shlesha. So you have various possibilities. But these various possibilities is just choosing. See, here I make a decision is to look, is there a triangle? So I can make this decision or not. There is a choice. There is a choice, it means the algorithm is non-deterministic. That is, I cannot just apply once and for all and read and get a unique solution. I have to take decisions. This is non-determinism. Okay? So at some point it may fail. If it fails, then I will backtrack. I will go back and try some other thing. Okay? But there is a finite number of such solutions. And then you get that in the end. Okay? Then you get the padas. Once you get the padas, I'm taking more time than I should, I'm sorry. But here we see all the operations. Once I have the padas, I can unpada them. I can take the pada and go back to the pratipadika. Yes, this is the inverse operation. See? Because in the pada lexicon, I can put indication of what are the parameters and what is the pratipadika that is used. So I can go back in my computation. So this is a stemmer here. Stemmer. It's also called lemmatizer. This is kind of pedantic. Stemmer means find the stem. Take the pada, find the pratipadika. That's what it means, stemmer. Devat. Devat, is it a noun? I ask, and it answers, yes. It lemmatizes, that is, I can find some pratipadika, deva, and some morphological structures that are such that by doing the pada computation on deva, I will get devat. There are two such possibilities here. Ablative. What is ablative? Singular, ekavach. Masculine, puns. And here, neuter, napumsaka. So these are the two possibilities. See? So when I have the pada, I know what are the possibilities in terms of pratipadika and in terms of morphological features. Okay? So I can go back and forth in my computation. I can compute sandhi, I can compute unsandhi. I can compute padas, I can unpada into pratipadika. So this is for nouns, adjectives, etc., but it was the same for roots, for verbs, dhatus. It's more complicated, you have more complicated morphology, but it's the same. If, oh look, Jagannath, as Venugopal, yes? From Sweet Orissa. So this will conclude my presentation. You know, there is more and more, but then you get the idea of how the reader operates. The reader will break into padas, then the lemmatizer will break the padas into pratipadikas, and so on and so forth. Then you get the explanation and you get the link to the lexicon. So this is some kind of overview of the general architecture of the system. What you have to remember is that the central piece is the lexicon, and the lexicon with all its information, and from that I compile all the data structures, all the algorithms, and that's it. Any questions?
Does the non-determinism, non-deterministic feature of the algorithm affect the speed?
Yes, because you have to compute many solutions. Okay? So speed and Lagawa is very important. Okay? So I wanted to explain this kind of problem by explaining how I recognize compounds. Okay? Because I gave this example from Panchatantra of a very long compound with 10 components. Okay? And then you have 1,000 ways of writing a binary tree and trying to interpret it as a binary compound. Okay? So you have to be careful, because if you have a sequence of choice, then it's exponential. Let it be, you know, if you have binary choice, then it doubles, then it doubles, then it doubles. Okay? So you have to think of this king and the chessboard. Okay? So you should not be too greedy, you should not be stupid like the king. You have to think. Yes? So if you have many choices, yes, it's going to be very expensive. So So you have to minimize the number of choices. Okay, and for that you look at the constraints of the problem so that you don't generate, crores of solutions. Yes, or you generate 1,000 solutions, and you look more constrained, and you have only 10 solutions, then we work more, then we'll have the right solution. Yes, yes, non-determinism is costly, and it's in some sense the main problem, because it's a problem of search. You cannot go directly to the solution. You have to find your way. And finding your way in an efficient way, this is the difficulty of the task. It's a difficulty for us also. It's not just for the machine. When you have /have poetry, it's hard. Yes, you have to work hard to find all the solutions.
What is the
Yes.
output rate? How much percentage it is giving correct answer? For the simple words and for /, like or compound words, big compounds.
The Sandhi Vicheda done this way is very fast. Okay, so you get the answer fast. You have a finite number of solutions, but you have choices. So if you're trying to input a big sentence, say with 20 padas, then this is going to take time and to take space also, because you have lots of solutions. Okay. So you have two considerations. One is completeness, and the other one is precision. You want to get all the solutions, yes, and you don't want to get too many extra solutions. Okay, so there are these two parameters that you have to watch. I cannot go into more details, but if you're interested, I can tell. I'm aiming at having completeness for simple text, because the completeness will depend on the size of the lexicon. Okay, so if the text is not too hard, if it's not Vedic, if it's classical Sanskrit, then there are chances that my lexicon will cover it. Also, there are more additional details, is that the lexicon may be generative. That is, instead of storing all the padas, you can store rules that will generate implicitly all the padas. Okay. So if you have a corpus whose vocabulary is covered by my Pratipadika lexicon, then I will find all the solutions, so it's complete. Okay? But the success rate depends on the constraint algorithm. Okay? And I can show you examples. Okay? I don't have a fully compiled set of figures and a fixed corpus. I'm working on that. I'm working on having some tools of evaluation and have non-regression analysis test. Then I will be able to tell figures. Yes.
What about Upasarga and Thakur? There are many possibilities.
Yes, that's a good question. So, this goes into a kind of controversial topic, is what is a verb? Okay. In the Western linguistic tradition, we would say that we have verbs that are from dhatus and upasargas before. Okay, and these verbs have various forms, all the conjugated forms. In the Paninian tradition, you tend to limit yourself to dhatus, to roots. Okay, and treat the upasargas separately. You don't build the dictionary of all verbal forms. Okay? So what you built is a dictionary of all upasarga sequences and a dictionary of all dhatu tinantas. Okay? And now you will separate a verbal form. You will separate the upasargas from the tinantas using sandhi vicheda. Okay? Using similar algorithm. Except that the sandhi between upasarga and tinantas is not exactly the same as the sandhi between padas in the sentence. Okay, you have retroflexion coming. Okay, so you have to know when you're breaking a verbal form after finding the upasarga sequence and looking for the tinanta, you have to know that you're not using the usual sandhi rules that are used in the sentence, but more because you have retroflexion. So it's a detail, but you have to take into the account this detail, and now you can separate the upasargas from the root. I can show examples. What about compounds? Compound is the same. You break compound by the same sandhi vicheda. Okay? So I don't have to store all compounds. There are infinite compounds. Yes, there is no end. There is no end. But these kind of algorithms, looking for things in finite structure, you can get some kind of infinite representation. Okay? If you have a big set, even infinite, if it has a regular structure, then you can represent it finitely. This is the basic idea. Okay? And I can illustrate this idea with a simple example. If you try to divide number 5 by 3, it's not divisible. Eh? It's greater than 1, smaller than 2. Oh, you make the computation, it's 1.6. After that, 6. After that, 6. Or we could go on until the end of the universe, saying 6, 6, 6, 6, 6, 6, 6, 6. There is no end. But it's regular. It's always 6. So, I write 1. I write 6. I say after 1 I have a 6. I say after 6 I have a 6. This is 5 over 3. Even though it has an infinite decimal representation, I represent it finitely this way, because it's regular. Okay? So, there are many tricks like that. I cannot do a full course of computer science in 1 hour, but you get the idea.